In this section, I will continue to talk about inferential network analysis. Now, in section 1, we talk about exploratory network analysis. We try to describe and understand the patterns in a network. Now, in this section, we focus on explaining the patterns in a network or use the patterns in a network to predict other variables. So therefore, we would like to study the relationship of a network with other variables. In understanding the relationship of a network with other variables, we will treat a network M as a variable and include it in a statistical model. So therefore, we could predict the network using other covariance information X. We could also use network to predict some other variables such as behaviors. To understand the relationship of a network with other variables, we needed to first select a probability distribution based on the outcome variable. We also needed to have a hypothetical model format, which will help us to address our research interest. Now, after we have a hypothetical model structure, we then needed to estimate the parameters in the model. We also needed to evaluate the model fit to understand whether the hypothetical model fits the data well or not. If the hypothetical model fits the data well enough, we then use the model to interpret the results. So in the following, for each of the model we talk about, we will first present the model and then talk about the estimation method. And then we also talk about how to assess the model fit and then interpreted the substantive meaning of the findings from that model. The first model we talk about here is called a stochastic block model. Now, in a stochastic block model, we treat the network model as the outcome variable. We would like to cluster the nodes into the blocks based on the connections. So that's the purpose of fitting a stochastic block model. So the primary form of a stochastic block model adopts a Bernoulli distribution for binary relationships. So in a Bernoulli distribution, the parameter is the probability P, right? Is the parameter. So the reason we adopt the Bernoulli distribution is because for binary relationships, we usually code it as 0 and 1. So therefore, we need to predict or model the presence of connections between two nodes. The probability of the observed network equals the joint probability of each edge. So therefore, the right side, we can notice that we multiply all the pairs of nodes. So pi Zij is the probability for the connections between the nodes I and j if their membership is Zi and Zj. Now, in the stochastic block model, there are a few things we needed to determine. The first, of course, is how many blocks in a network. So this is the number of blocks. Now, the second thing is that given the number of blocks, what's the probability for the presence of connections between two nodes? Now, stochastic block model assumes that the probability for the connection between two nodes purely depends on their block's membership or their class membership. If two nodes belong to the same block, for instance, if a pair of nodes are in block 1, the chance for them to connect is fixed, is the same value. For all nodes in the same block, the chance for them to connect is the same, is pi 1, 1. For instance, for all the nodes in block 1. Now, for all the nodes in block 2, the probability for them to connect is pi 2, 2. Now, for a node starting from class 1 connected to another node in class 2, it's pi 1, 2. For a node starting from class 2 and connected to another node in class 1 is pi 1, 2. Now, for a symmetric relationship, for a relationship has no direction, pi1 2 equals pi2 1. Now, therefore, stochastic block model assumes that the probability to connect purely depends on the class membership. By fitting a stochastic block model, we are able to understand the number of clusters and the probability for them to connect, and also the class membership. So therefore, we needed to get the pi estimate and also get the predicted membership. We also need to select the number of blocks. To fit the model, we could use EM algorithm. When we use the EM algorithm, we first need to tell the algorithm how many clusters we consider. So therefore, we first need to predetermine the number of clusters, tell the system, oh, we consider 2 clusters. And then the EM algorithm will first initialize the model parameters, including the probability pi and also the class membership. And then they update model parameter and then update the membership and do those iterative procedures. How do we know how many number of blocks in a network? We actually could take a model selection procedure. We could actually vary the number of clusters, choose 1 cluster, 2 cluster, 3 cluster, 4 cluster, and then use the EM algorithm to obtain the pi estimate, obtain the class membership estimate. And then, of course, we have estimated the likelihood. Then we could actually compare the likelihood across those different number of blocks. We choose the one with the greatest integrated classification likelihood. So the one with greatest likelihood will be the one we choose to use. After we select the number of blocks, then we could also extract the corresponding probability matrix and also class memberships, and we use them to interpret the results. In the following, I will use a simulated network to illustrate how to fit a stochastic block model. So this network is simulated from a stochastic block model with 3 blocks. And the within cluster probability is 30, and the cross cluster probability is 0.2. Which means that for nodes within the same cluster, the probability for them to connect is 80%. Now, for the nodes from different clusters, the probability for them to connect is 20%. So therefore, we can notice that there are 3 blocks in this network with 90 nodes. Now, when we fit the stochastic block model, the question is, will the model selection procedure really detect the 3 blocks? That's the first question. The second one, will the probability matrix pi will be recovered, or will we get the estimate close to the population value or not? That's the second question. So therefore, we will vary the number of clusters, different number of clusters, and then fit the stochastic block model, and then choose the number of clusters with the greatest likelihood. Now, how do we fit this model? We can use the R package blocks models and then use the function BM Bernoulli because we consider binary relationships. Then we save the fitting model into object M stochastic block model, and then we can extract all of the estimates, including pi estimate and also the likelihood, as well as predict membership into a new object, right? Into a new object. So then we could also extract all those classification likelihood, and we choose the one with the largest ICL. So the number of clusters associated with the largest ICL will be the one we use for model interpretation. And then we also extract the corresponding membership and the corresponding pi matrix estimate. So those can be implemented in R, and all the code are also attached to the course web page of this workshop. Now, based on SEL, Q equals 3 has the best model for it. So therefore, we interpret the model using Q equals 3. So when Q equals 3, the pi matrix is a 3 by 3 matrix. Now, the first element is the probability for the nodes to connect if they both belong to cluster 1. This is the probability for them to connect if they both belong to cluster 2. This is the probability for them to connect if they both belong to cluster 3. Then each other element of diagonal describes the probability for a row cluster connected to a column cluster. So remember that in the population or in the data generation model, the diagonal elements are all 0.80, right? And we found that the estimated probability on diagonal are close to 0.80. Now, in the data generation model, all of the diagonal elements here is 0.20, and we can notice that the estimate also close to 0.20. So therefore, recall that this network size is 90, right? So we can expect that if the network size is larger, probably the estimation going to with even less bias. We could also obtain the predicted class membership and then compare the misclassification since we know the true membership. Now, recall that, when we fit a stochastic block model, we would like to find the communities within a network. And also, this model assumes that actors or nodes within a block share the same probability to connect with actors from the same or from a different block. So therefore, it means that nothing matters about the connection, only the block membership matters about whether two nodes or two actors will be connected or not. This is a very, very strong connection. In practice, actually, many covariates could explain the formation of connections. So therefore, in the following, we're going to introduce another model, which could incorporate covariate information to predict the probability for the existence of a connection between two nodes. The second model is latent space model. Different from stochastic block model, latent space model include covariate information to explain the presence of social relations between two actors. So therefore, for the binary relationships, the latent space model is a log linear model, follows Bernoulli distribution. So Mij is the connection between I and J, actor I and Ij. So Mij equals 1 is mean that they are present connection, and Mij equals 0. It means the absence of an connection. So therefore, Mij follows Bernoulli distribution with pi ij. Now, log odds of pi ij. This is a linear combination of a bunch of edge covariate, edge level covariate xij. So alpha is the intercept, beta is the coefficient of the edge covariate. So xij, we could include multiple edge covariates. Now, in the latent space model, there is another very important component, which is the latent space. Now, latent space model assumes that each actor hold a position zi in a latent Euclidean space with d dimensions. So each actor holds a position there. Now, some actor will stay closer to each other. Some others will stay relatively further away from each other. So therefore, the closeness of two actors in the latent Euclidean space predict how likely they form friendship or they form connections in the manifest social network. In the latent space model, they use the distance Dij. Dij is the Euclidean distance between the two actors in the Euclidean space. So Dij is larger, it means that the two actors stay away from each other, right? They are less close. And Dij is smaller, it means that they stay closer to each other. So therefore, when we subtract Dij, it means that the larger the distance, the less likely for them to connect. However, the smaller the distance, the more likely for them to connect. So therefore, the latent space model actually assume the principle of homomorphy. Principle of homomorphy states that similar latent positions promote connections. So if two students stay closer in the latent space, right, they share similar latent positions, they have a higher chance to connect. That's the first assumption. Now, the second assumption is conditional independence. Conditional independence assumes that given the covariate included in the analysis and given the latent positions Z, the joint likelihood of all the edges or of the entire network can read as the product of the likelihood of each diide. This only be true when the conditional independence is satisfied. So this also need that the model we fit to the data is a true model. All the relevant covariate are included in the analysis. Now, to estimate this model, actually, we could either use maximum likelihood or Bayesian estimation method. So this actually has implementation in our package, ERGMM. So maximum likelihood is basically we would like to find a set of model parameter estimate, alpha hat, beta hat, and also latent position estimate, which maximize the log likelihood. We already have the likelihood function, and then we take logarithm. We got the log likelihood. So maximum likelihood estimator is basically those set of parameters values which maximize the log likelihood. We can use Newton type of algorithm, right? We can use YAML algorithm to obtain that. Now, the second type of approach is Bayesian. So different from maximum likelihood, which directly maximize the log likelihood, Bayesian is try to obtain a posterior distributions of the model parameters. So conditional on the covariate, conditional on the network, we get a posterior distribution of model parameters. Now, based on the Bayes theorems, the posterior distribution proportional to the product of likelihood and the prior. So therefore, to implement the Bayes method, we also needed to specify priors for model parameters, which includes the latent positions. So usually for regression coefficients, right, which has no direction, we could choose normally distributed priors. For latent positions here, we could also choose normal priors. To get a posterior inference, we would like to get a posterior distribution. However, very often we do not have an analytical form of the posterior distribution, or the posterior distribution does not belong to any known family of distributions. So therefore, how could we understand about the posterior distribution? So we could actually, using MC algorithm or procedures to obtain a chain of samples for each parameter. We use the set of samples we sampled for each parameter to approximate the posterior distribution. So therefore, we want to make sure that the samples we we used are from the posterior distribution. So therefore, we needed to do convergence diagnosis. We needed to check whether our chain convergence or not. We need to investigate the potential autocorrelations among the samples we use. We also need to determine how long we would burn out at the beginning of the chain. So those are all the work about the Bayesian estimation methods. So I'm now going to use the empirical example to illustrate both the maximum likelihood and the Bayesian estimation method. So we could fit the latent space model to the college friendship network. So we first fit the model with no edge covariate. So what's going to predict the network? The only information to predict the network is latent position. So we only use the latent position Z to predict the probability of the formation of connections between two actors. So therefore, latent position Z itself explains all of the dependence within a manifest social network. So we first obtain the estimate using maximum likelihood. So we could implement the model in R using the function ERGMM. The left side of the tilde sign is the network object. So this here is we can input the college friendship network over there. And the right side, we can tell what's the dimension of the Euclidean space we use. If we use 2 dimensions, then we just tell the function d equals 2. Now we tell the function we would like to obtain a maximum likelihood, then we choose MLE here. And then the family is Bernoulli because we have binary relationship or binary network. We then save the fitted object to a name fit ML. Then we could extract the position estimate, right? Because when d equals 2, each of the position has 2 components or 2 components, right? The first component is the score along the x-axis. The second component is the score along the y-axis. So therefore, each actor will have 2 scores for the latent positions. We could also have the intercept estimate for this situation when we fit the model to college friendship network. Alpha hat is 2.65. This talks about the baseline connection. When 2 persons share exactly the same position, then how likely they connect to each other. So that's the baseline probability for 2 actors to connect to each other if they share exactly the same latent position in the latent space. We could also fit the model using Bayes, and then we use the same function, still include the 2 dimensions, and then the default one is Bayes. Then we need to set up the control factors. For instance, how many samples we want to keep in the analysis, how many iterations at the beginning we will discard as the burn-in period, and what's the thinning intervals. So after the MMC algorithms finish or complete, for each of the parameters and also the latent positions of each actor in the network, we have a Markov chain. Right? Then we need to do convergence diagnosis, use MC diagnostics. If your chain converges, then we can use the remaining samples to do analysis. Now here, I would like to contrast the latent position estimate obtained using maximum likelihood and obtained using Bayes. So the left side is the plot of the latent positions of students in the latent space. Each bubble in this plot is describe the position of students in the college friendship network. So and the gray edges connecting them present that there is connections in the network. We can notice that there are 6 clusters, right? Why we call it 6 clusters, because we have 6 groups of students. Within those groups, they stay closer to each other. Now, on the right side, we also plot the positions of the students in the latent 2-dimensional Euclidean space using their latent position estimate, which are obtained from Bayes framework. Now, we can notice that, the patterns in those 2 plots are similar to each other. On the right one, we also have 6 blocks or 6 clusters. And we can also notice that look at these blocks and look at this block, they are supposed to be the same one. However, the latent positions are smallly or slightly different from each other, right? So if we look at this block and this block, they're supposed to be the same block. However, the latent position estimate are also slightly different. Now, this slight difference between the latent position estimates is due to the inclusion of priors in the Bayesian framework, because prior distributions are used, and it could influence the position estimate. Otherwise, those 2 methods give very, very similar position estimates. So in those 2 plots, we do not include any covariate to explain the presence of social connections in the college friendship network. The only factor that predicts the presence of social relations is the latent positions. So therefore, latent position itself explains all the dependence within a network. So all the dependence within a network is explained by the latent positions. Now, in the next, we're going to try to include the edge covariate in the analysis. To demonstrate how to include the edge covariates, we will consider 2 edge covariates. The first one is SGPA. We create an edge covariate by getting the difference of the GPA of the 2 nodes in a diode, and then get the absolute value. So therefore, the larger this covariate, it means that the more dissimilar in terms of GPA of that 2 students. We also define the edge covariate agenda of a pair of nodes, right? So as agenda ij equals 1 if student I and j share the same agenda, 0 otherwise. So by investigating the coefficient of S agenda, we are able to know how the same agenda going to promote friendship compared to different agenda. To include the edge covariate analysis, we could use the command edgecov, and then in the parentheses, we put the variable name as GPA, edgecov as agenda, and then we also include the Euclidean space d equals 2. And then if we use Bayes, then we tell the setup of the Bayesian algorithm, sample size, and brain, and the thinning, etc. to go on. This is the summary, or this is we print out of the Bayesian inference, the estimation obtained using the Bayesian method. So we have the intercept estimate, which is 2.19483, which is quite different from the previous one when there is no covariate included in the analysis. Now, the coefficient of SGPA is negative 0.2 around, right? And the coefficient of S agenda is 1. Now recall that the larger XGPA, the more dissimilar or the less similar of the 2 students in terms of GPA. Basically, larger SGPA means that those 2 students are more different from each other in terms of GPU. Now, the coefficient is negative, right? It means that actually more different GPA actually decrease the probability for two students to form a friendship. Similar GPA promote friendship. Now, as gender is positive, right? So as gender is 1 for the same gender students, or for the two students with the same gender. Now, it is positive, mean that the same gender actually promotes friendship. So for the Bayesian framework, we could also report the 95% credible interval. So the lower 2.5 percentile, the upper to 97.5 percentile. Here is the plot of the latent positions with covariate and without covariate. They both are obtained from the Bayesian estimation method. We can notice that, there are also some differences, right? So we still have 6 blocks. However, the spread of the latent positions or the spread of latent clusters are slightly different. Now, those differences are more likely due to the inclusion of covariate. Because without the covariate, the latent positions reflects all the dependency in a manifest network. However, with covariate, the latent positions only reflect those dependence that is not explained by the covariate yet. So therefore, the information those latent positions try to demonstrate are different in those two situations. So therefore, the latent positions are slightly or are different. We just fit the latent space model with and without covariate. Now, what are the model assumption and which situation we could fit a latent space model? Now, by fitting a latent space model, you assume that there is a low-dimensional latent space, and each actor holds a position in it. Second, the actors' positions in the latent space is planned propensity for them to connect in the manifest social network. So therefore, if two actors stay closer to each other in the latent space, then their log odds is larger. The probability for them to connect is larger. If two students stay further away from each other, so the log odds actually smaller, then the probability for them to connect also smaller. So therefore, by fitting the latent space model, the principle of homomorphy is also assumed. When fitting latent space model, we need to determine the dimension of latent space D. So in practice, D equals 2, a small d such as D equals 2 is already able to explain a reasonable amount of dependency in a network. Now, however, we could also adopt the model selection procedure by varying D and then compare the fit indices, such as BIC and DIC. However, the power of those fit indices to detect the best number of dimensions is still not well explored yet. So therefore, we suggest you do sensitivity analysis for your model when you choose to use BIC or DIC as a model selection indices or model comparison fit indices. Now, the latent space modeling framework we present currently focuses on undirected binary social network. Now, the model actually can be extended to directional relations using projection model. It could also include random effects model, such as sending and receiving effect of each actor. We just fit both stochastic block model and the latent space model. Both models is try to predict the probability of network and by predicting the probability for the presence of each edge. So they both try to predict the formation connections between two nodes. So the stochastic block model assumes that the membership matters for the connection. There is no other covariates will help to explain the formation. Nodes with the same blocks share the same probability to connect. No external information used for predicting the network. Now, latent space model is more flexible to include the covariate to predict the formation of edges between two nodes. So it includes the edge level covariates. It also allows for the different probabilities for pair of nodes to connect. So latent space model in terms of the probability to connect is more flexible than stochastic block model. Now, both models can use to do clustering. So latent space model predict the class membership directly as a part of the model estimation procedure. So therefore, for each of the node, we will output a membership. Now, for latent space model, although we didn't output a membership, we could obtain the latent position estimate, and then we could use obtain the latent positions to do clustering. Now, when we look at back to the plot of the latent position estimate, we can notice a bunch of clusters. So therefore, both models can be used to do clustering. So now, after a short pause, I would like to switch to a different framework. In this framework, we aim to combine the network model with the psychometric model. We would like to connect a network model with the confirmative factor model. So therefore, we just call our model is latent factor space model. So basically, in this model, we will have both a measurement model and a network model. So the motivation for proposing the latent factor space model comes from a very classical research questions, whether birds of feather flock together or opposite attract. This is actually the same as the principle of homomorphy, because many natural relations are assumed to follow the principle of homomorphy. So whether birds of feather flock together or opposite attract. So therefore, to answer these questions, we needed to identify the factors or the reason that could help us to explain the formation of friendship among students. So therefore, we would like to identify the factors predicting the friendship among students. Now, the candidate predictors, when we collect the data, include the gender information, academic performance information, smoking behaviors, and the personality, even like loneliness and the depressions, those health behaviors. So therefore, we would like to test whether those informations actually could predict the friendship among students or not. Now, you may notice that there are some of those variables which are latent constructs, which should be measured using a measurement model. So therefore, we need to include the measurement model in analyzing a social network. This is the mathematical model. We call it the latent factor space model. So the latent factor space model actually contains two parts model. One part is measurement model. The measurement model is a confirmative factor model. For those confirmative factor model, we have latent factors eta, and we also have indicator data for the latent factors. And then here lambda is a factor loading matrix. And then phi and psi are the covariance matrix of latent factors and the covariance matrix of residuals. So the highlighted blue part is a measurement model. Now, in the factor model, we would like to use the latent factors, such as personality factors, to predict the network. So therefore, Dij here is not the distance in the Euclidean space, but the distance between two factor scores of student I and student J. So gamma is the coefficient of latent personality distance. Here we can freely let the data speak up the direction of gamma. Gamma could be positive, could be negative. So Dij here is the Mahalanobis distance, study the difference between those two personality vectors. Now, because those two personality vectors are allowed to covariate with each other, so therefore we computed the Mahalanobis distance to account for the potential covariation between them. Now, this is called the latent factor space model. We have a factor model, which give us the information about the latent factor scores. We also have a logistic model, which used to help us to predict the presence of connections within a network using the latent factor scores. Here we use an example to illustrate the latent factor space and also the distance for two students in that space. Now, when we fit the latent factor model, we could fit a confirmative factor model by fitting the model in addition to the model parameters such as factor loading estimate and also the covariance matrix estimate. We could also obtain the factor score estimate. We could obtain eta hat. So therefore, for each student, we could obtain a factor score such as personality factor score estimate by fitting the CFA to the personality data. So for instance, when we plot the factor score, extrovert and imagination, each bubble in the plot represent a student's position in the space formed by extrovert and imagination. So some students have a relatively low extrovert score on this side, but high imagination score, such as here. Some students has both a high imagination score and extrovert score. Some students have low imagination score, right? Very low imagination score, and some high extrovert score. So basically, in this plot, each bubble is represent the personality score on extrovert and imagination of that students. Now, when we have a space, we need to define a metric. For this personality space, the metric we use is the Mahalanobis distance, which describes how similar two students in terms of extroversion and imagination. So smaller d, similar, and larger d, dissimilar. Now, to estimate this model, actually, we developed both two-stage maximum likelihood. Now, the reason we adopt the two-stage maximum likelihood because this is easy to implement in the existing software. And many researchers are familiar fitting a CFA model, right? And obtain factor score estimate in our head. So that's the first stage. In the first stage, we fit the CFA model to the personality data and obtain model parameter estimate and also obtain factor score estimate. Now, in this stage, we need to evaluate the model fit, just as a standard structure equation model. We hope that the RMS EA less than 0.05 and CFI larger than 0.95. Now, after we obtain the factor score estimate and also the factor covariance matrix estimate. In the second stage, we can use those information in the logistic regression directly. So in the second stage, we just use the estimate factor score in the analysis. So in this stage, we need also to evaluate model fit, and we can use difference-based indices. Now here is the result from stage one. Stage one, we fitting a confirmative factor model, right, to the personality. For instance, one factor is extrovert and the other is imagination. Each of them has 4 indicators. By exploring the factor structures of this specific data set, we also detect the cross-loadings from imagination to the item I keep in the background and also correlated residuals. So this is the final structure we extract, and we obtain both the factor score estimate. For each student, we obtain 2 scores, one for extrovert and the other is for imagination. And then we also get the factor occurrence matrix estimate. And for this stage, we evaluate the model fit and with the RMSEA around 0.04 and the CFI is larger than 0.96. So therefore, for this stage, this is the final model we use. And we obtain both the model parameter estimate related to measurement model and also the factor score estimates, which will be used in the second stage. Now, in the second stage, in addition to Euclid to Mahalanobis distance of the factor scores D, we also include a bunch of edge covariates. The first one is edge covariate related to gender. Again, if 2 students or 2 actors share the same gender, we code that edge covariate as 1. Otherwise, we code it as 0. We also compute the GPA, absolute value difference. In addition to those 2 covariates, we also know that, in this group of students, in this social network, students have a homeroom. So therefore, students from the same homeroom, very often, they have more chances to interact with each other. So which is going to lead a higher chance to build a friendship. So therefore, we would like to control the classroom membership. So we define the classroom membership covariate if student I and J are in the same class, then we code it 1. Otherwise, we code it as 0. We also compute the Mahalanobis distance D. We then include the Mahalanobis distance D and the 3 edge covariate to the logistic regression model. We obtain the coefficient estimate. So for the first one, recall that the first one related to gender, right? Same gender coded as 1. The coefficient is positive. So it means that the same gender diide have a higher chance to cross than the diide with no students of different gender. So therefore, same gender promotes friendship. The second one is GPA, although it's positive, but here is not significant. The third one is class membership, is positive, and also very significant. It means that the same class really, really helps to build a friendship. That makes sense, right? Because same class students have more opportunity to interact with each other and then build a friendship. Now, the latent Mahalanobis distance of the personality scores has positive, however, is not significant. So by fitting this model, we also have a different type of measures, such as AIC and the difference for the residuals and difference for the non-models, which can be used for model selections in later. Now, the 2-stage method fit the model. First, fit the measurement model. Second, fit the logistic model. Now, because we use 2-stage, it's quite flexible. Now, in the second stage, in addition to fit the linear model, with D as a predictor. We could also fit the higher order model with D square as predictor and D to third power with predictor. By fitting the model with the different degrees of latent distance, we are able to explore whether the relationship between the latent personality distance and the log odds is linear relationship or quadratic relationship or cubic relationship. So therefore, we are able to explore more complex structures by fitting the higher order model. Now, because all the other covariates are the same, when we include the D square in the analysis, we also have a D. And when we include the D cube, we also have a D and D square in the analysis. So therefore, the lower model are necessitated in the higher model. Then we could use a likelihood ratio test to help us to compare different model fit and then detect the best fit model. So in the following, I'm going to illustrate that. So in this part, we talk about the latent factor space model, right? Which is a model connect measurement model for the actor attributes with the logistic model for networks. Now, we could fit this model or estimate this model. It use both two-stage maximum likelihood and Bayesian. And in the current workshop, we introduce how to use the Bayesian step by step. We also develop the Bayesian procedures to estimate this model. Now we fit this model to the empirical college friendship network. And at each stage, we need to evaluate the model fit. At the first stage, when we fit a CFM model, we can use the structure equation modeling techniques to evaluate model fit. Right, in the second stage, we fit logistic regression. We can use the Davis-based or information criteria-based indices to help us to assess model fit. Now, this framework can be extended to ordinal relations, so weighted network, and also network with directional relations. So those are both framework already developed. So the next or the last model I will talk about is network mediation analysis. So network mediation analysis aim to study the mediation role of a social network on the relationship between two variables. We would like to know how your social environment, right, mediate the effect of I of A on D. So let's first review a little bit about the simple mediation analysis. Simple mediation analysis is a regression-based approach. So it is a trivariate system. So in this system, there are three variables, X, Y, and M. X is the independent variable, Y is the dependent variable, right? So X predicts Y. So C will be the total effect. The total effect that I impact Y. So M is the mediator. So we have regression from independent variable to mediator, and meanwhile, we also have the regression model from both the independent variable mediator to the outcome variable. So therefore, by fitting this trivariate system, we are able to get the total effect estimate C hat. We could also get the direct effect C prime hat, which is the effect of X on Y after controlling the mediator. We could also get the indirect effect, which is the effect of X on Y, however, passes through M, so which is the product of A hat and B hat. Now, by fitting this trivariate system, we are able to estimate those three effects. However, we need to note that it's important to note that the detected indirect effect A hat B hat is not necessary to be mediation effects, right? So even there is no mediation process involved, when we fit the model to 3 variables like this, we're still able to get an estimate for A hat B hat. But this estimate A hat B hat is not necessary to mediation effect if the M is not an actual mediator. So therefore, we need additional assumptions in order to make sure that the indirect effect is mediation effects. So this is the diagram of the mediation model, right? It's a cherry system. So this demonstrates the total effect from S to Y. This demonstrates the indirect effect of A first to M and then to Y, right? A times B will be the indirect effect from A plus M to Y. And then we also have a direct effect, C prime, after controlling the mediator. Now, what is the assumption needed in order to make the detected effect A times B is mediation effects? Here is the assumption. So in order to make sure that the detected effect A times B is median effect or is causal, we need the path S to M to Y. So this is S to M to Y. We need it to be causal. Now, what does causal mean here? In order to make it causal, we needed to eliminate the potential effects of a third variable. We must make sure that there is no third variables to confound or lead to predicts X, M, Y. So basically no unmeasured confounders for the X and the M relationship, no unmeasured confounders for the M and Y relationship, and no unmeasured confounders for the X and M relationships. So therefore, if we look at the diagram, it needs that for the path between X and M, there is no unmeasured confounders. From M to Y, there is no unmeasured confounders. From X to Y, there is also no unmeasured confounders. We now introduce the proposed network mediation model. The proposed network mediation model, for instance, aims to study the effect of gender on smoking behaviors. So the smoking behavior, which is coded as 0, 1, which is the dependent variable. Gender is the independent variable. We would like to study whether there is gender difference in terms of the smoking behavior. Now, the mediator is the friendship network. Recall that, for each of the nodes in the network, we have one data point for gender. We have one data point for smoking. But however, we have n-1 data point for the social relations. This is because each actor involves in the relationship with every the others in the network. In the friendship network, we have 165 students. So therefore, we have 164 data points, which describe the relationship of A students with all the others. Now, simply we can notice that the data dimension mismatch. So the mediator network and the gender and the smoking, they do not share the same dimension. The mediator has way more higher dimension than gender and smoking. Therefore, we need to try to find a method that could make the dimension of gender and network and smoking match each other. So therefore, we either need to down dimension, reduce the dimension of network, or we could use it to increase the dimension of gender and smoking. In the current formulation, we choose to reduce the dimension of a network. I will explain how. Now, let's recall or revisit latent space model. Latent space model basically maps each actor into a low-dimensional latent space. So we try to find the low-dimension representation actually of a network. We use the latent positions with d dimensions. Those latent positions represent or describe the dependency in a network. So therefore, the latent space is a low-dimension representation of the manifest social network. So by fitting the latent space model, we are able to obtain each node or each actor a latent position score. Those latent position score actually explains the dependence of that students with all the other students in the network. So therefore, we are thinking we could use the latent positions actually as the actual mediators in the network mediation model, because the latent positions integrate or summarize all of the informations of the dependency informations in a network. So based on this rationale, we propose the following model. In the proposed network mediation model, we have a latent space model, which help us to find a low-dimension representation of a network. So we use Z. And then we have the mediation model with the Z as the actual mediator. So those two parts model together form the network mediation model. So in this model, if we have D dimensions, right, then when we regress Z latent positions to X, we have D intercept. We have D coefficient X to latent dimensions. We also have D coefficients from the mediator to the dependent variable Y. So therefore, I1, A, B here are all vectors with D elements. However, I2, the intercept, and the direct effect C prime are still a scalar. To estimate this model, we need to obtain those coefficient estimates. We could fit both the latent space model and also the mediation model in one framework using the Bayesian estimation method, which could be run in JAX. Now, here is a path diagram of the network mediation model, right? We have the latent space model part, which use the latent positions to predict the network. Or by using the network information, we could understand the latent positions. And then the latent positions involved in the mediation path directly. They are the actual mediators. So the latent space is a low-dimensional representation of the high-dimensional network. So we can now, we could match the dimensions of the data. In this proposed network mediation model, there are a few effects we are able to test. The first one, because we have D mediators, right? So therefore, along each dimension, we are able to get an indirect effect estimate. For instance, along the first dimension, we are able to get A1 multiplied B1 hat. Along second dimension, we are able to get A2 multiplied B2. Along the third dimension, we are able to get AD multiplied BD. So along each dimension, we are able to get an indirect effect of a single dimension. Now, however, we needed to note that those indirect effect of a single dimension has no substantive meaning. This is because we are able to label each dimension. In terms of network, all those dimensions are equivalent. And also due to the rotation, reflection, and translation, those latent positions actually are not unique. They could rotate, reflect, or translate. So therefore, the effect along each dimension is less of a substantive meaning to us. Now, we could actually also get the total indirect effect along all dimensions. So therefore, we get the sum of all those effects along dimensions. And we also get the direct effect estimate and also the total effect estimate. Now, we have shown through simulation study that the total indirect effect is actually well defined and also can be covered. And the total effect is also recovered, the direct effect also. So therefore, in the proposed network mediation model, we will obtain the total indirect effect estimate, direct effect estimate, and the total effect estimate. When fitting the proposed network mediation model to an empirical data set, there is one thing we need to determine. We remember that we use a latent space model to extract a low-dimensional space, right, to reduce the dimension of the network. Then the question is, how many dimensions we need? How many dimensions will explain or account for sufficient dependency in a network? So therefore, we need to determine. Now, to determine the dimension of the latent space, we actually could fit the latent space model to the network data. We can vary the dimension and then to get the BIC. Now, for the current network, college friendship network, we found that when D equals 5, when the latent space has 5 dimensions, there it is has the lowest BIC. Therefore, when we explain the result, we will use D equals 5. We could obtain the estimate of this model using JAX. So we could fit the entire model, the latent space model, as well as the mediation model simultaneously in the JAX. And then we also need to specify priors and check the convergence. So therefore, I won't talk about this in detail. And the model for this model is also available on the course website. I'm now going to explain the results. So we fit the latent space model with 5 dimensions. We obtain the total indirect effects. We obtain the direct effects. We also obtain the total effects. Now, we found that the total effect is negative. Now, recall that in this model, the female students, the female is coded as 1, the male is coded as 0. Therefore, this means that female students is less likely to smoke or has lower smoking score. Now, the total direct effect also negative. It means that such kind of part of those difference is due to the network, friendship network. So therefore, male students smoking more part is actually also due to the network. Due to the network, social network, they smoke more. Now, the direct effect also negative. We check the convergence of each chain using weak statistic. We hope that the statistic is within -2 to +2, right? Then we can conclude that they are convergence. We also obtain the 95% credible interval. They all exclude 0. The proposed network mediation model itself cannot justify whether there is a causal relationship or not. The model itself can be used to evaluate the mediation effect to estimate the mediation effect if there is a causal relations based on theory. So therefore, we also need additional assumptions in order to make sure that the detected effect is mediation effect. So what assumption need? So we need that there is no unmeasured confounders for the XY relation, XZ relation, and Z to Y relation. These are similar to those used in the simple mediation model. If we want it to be a causation, then we need those 3 no unmeasured confounders assumption. Now, in the network mediation model, we have more than one mediators, right? Because we have d-dimensional latent positions involved in the mediation path. So therefore, we have actually d mediators. Therefore, we need one additional assumption. There is no direct path across latent dimensions. So those are the assumptions needed to make a causal model, to make it a causal network mediation model. So that's the end of this workshop. All of the data set used in the demonstration of the models and our code used in extracting those results or tables or plots are available on the course website. So feel free to reach me out for any questions you have. And thank you again for your attention.